Ladies and gentlemen, we want to take a moment to extend our thoughts and prayers to all those suffering directly and indirectly from the COVID-19 global pandemic. The name sounds like something out of communist Russia in the 1940s. Come to think of it, the supermarket has that kind of feel as well. People are scared and they should be. Everyone could be a carrier and infect you and your loved ones, especially if they have underlying disease like diabetes, hypertension, and many other, all caused by one thing: insulin resistance. Now is the time to learn how this condition invades your entire body and causes metabolic mayhem.
Obesity is also a key indicator, with the chances of dying increasing by 37%.
Pathological insulin resistance affects all tissues, but the problem really begins in the fat tissue. Specifically, it starts with having too much fat for your body to safely handle. If you've ever seen someone with type 2 diabetes, the end stage of insulin resistance, this makes sense, since they're almost always severely overweight. Clearly, fat causes this disease. Only one problem: not everyone who is obese has type 2 diabetes, and not everyone who has type 2 diabetes is obese. While fat is clearly involved in the development of insulin resistance, it's not as simple as the more body fat you have, the more insulin resistant you are. The story is a bit more complicated than that. You might have heard before that you cannot get rid of fat cells. You can only shrink them by emptying out the fat within them. Now you might be thinking, oh damn, well that really sucks. But you need to always remember, your body is way smarter than you are. So why is this? To prevent insulin resistance. Fat tissue is not just there to store energy and to ruin your self-esteem. It's a buffer for nutrients and has several important signaling roles in the body. Essentially, each of your fat cells has a limit to how much fat it can store. The more you fill these up, the more resistant to insulin you become, because the energy uptake into the fat cell is an insulin-dependent process. If the cell becomes resistant to insulin, it will resist incoming energy. If this happens to one cell, it's no big deal. That one cell rejects some fat so another cell can have it. That's not a disease, that's an efficient allocation of resources. However, when all of your fat cells start rejecting fat, that's when you have a problem.
Where do they go?
But remember, this is all dependent on how many fat cells you have, the personal fat threshold, which is the amount of body fat you can safely store in the adipose tissue. The more fat you can store, the more cushion you have in terms of putting on weight. Under certain conditions, it is possible to sprout new fat cells, and this is protective against insulin resistance. This concept of storage capacity determining insulin sensitivity is illustrated in one study, which looked at obese women and separated them into two groups. One group either had diabetes or had a higher risk of diabetes because of certain blood markers, a few of which we addressed in our last video. The other group did not have diabetes and did not have these markers of insulin resistance. Both groups had the same amount of fat mass, so what was the difference? The number of adipocytes, fat cells, was significantly lower in those that were insulin resistant. These cells were also significantly larger, indicating that they were at or near their carrying capacity. Same amount of fat, less places to store it, more insulin resistance. This is further proven by a mouse study, which genetically modified a group of mice to express more adiponectin, a hormone that stimulates energy uptake into adipocytes. When mice lack that adiponectin gene, they are susceptible to fatty liver disease and insulin resistance. Mice that express more adiponectin see the opposite. While they do in fact get fatter, they also have lower levels of inflammation and lipids in the blood and liver. The extra fat they were able to uptake in their adipose tissue was protective even though they got fatter from it. One more example to really drive this home is people with lipodystrophy. This is a condition where individuals have incredibly low numbers of adipose cells, and consequently, a large proportion of them have insulin resistance and type 2 diabetes. When lipodystrophic diabetic mice are implanted with new adipose tissue, a new safe place to store energy, their insulin sensitivity returns to normal and their diabetes gets cured. In fact, this is how some diabetic medications work, by artificially increasing the body's fat storage capacity. Of course, the way to do this naturally is just to lose body fat, but they don't want you to know that.
If you took Avandia prior to October 26, 2007 and had a heart attack, stroke, congestive heart failure, or liver failure, you may be entitled to compensation. The statute of limitations is running out to file a lawsuit. Studies have shown that Avandia increases the risk of heart problems.
As the adipose tissue continues to become more stuffed, it becomes more resistant to the signaling effects of insulin, so the body has to compensate and pump out more insulin. Eventually, this leads to elevated levels of insulin even while fasted. What does insulin normally do in fat tissue? It promotes uptake of energy into adipocytes and suppresses the release of fatty acids into the bloodstream. However, in insulin-resistant individuals, the high levels of insulin are enough to continue to allow more fat into the cell, but are not enough to keep that fat in the adipocyte. Since the cells increase the amount of fat they take up and the amount they release, the adipose tissue will essentially hit a wall where it can no longer store fat, but the insulin resistance will worsen. This means the body will continue to pump out more insulin but become progressively more resistant to it. Additionally, the elevated free fatty acids in the blood resulting from insulin not being able to keep them in fat cells will induce insulin resistance even further. The inflammation resulting from the increased fat cell size will increase lipolysis, meaning more free fatty acids in the bloodstream, which causes more insulin resistance. The inflammation will also directly lead to diminished insulin signaling by partially deactivating the insulin receptor. At this point, the fat tissue is at war with itself, and the problems have only begun. In the hypothalamus, insulin signaling normally works to suppress appetite, but with the cascade of insulin resistance promoting factors invading every part of the body, insulin can no longer do its job in the brain. The body, by being chronically overfed, ironically is now convinced that it is starving, which will only make the problem worse. So now the fat cells are overflowing with fat and the body is in a hyperinsulinemic state trying to put all this energy somewhere, but it can't. This leads to fat being shoved onto some tissues that aren't meant to store fat. It begins with the liver, which acts as home base for metabolism. The bloodstream is filled with free fatty acids and triglycerides, so the liver will have a significant uptake of these substrates. The liver gets overwhelmed with energy, and along with the systemic inflammation that has been developing, results in incomplete lipid metabolites, ceramide and diglycerides. These also signal the deactivation of the insulin receptor, leading to insulin resistance of the liver. In most tissues, glucose needs insulin to enter cells. However, the liver has receptors that can take up glucose independently of insulin, meaning there's a high concentration of glucose in the liver. Insulin also allows glucose to be stored as liver glycogen, but with deficient insulin signaling in the liver, this does not happen. Interestingly, another insulin-dependent pathway that creates fat from glucose does still work. Now there is even more fat buildup due to the glucose being allocated to one of the only tissues that doesn't need insulin to take it up. This accumulation worsens the high triglycerides and insulin resistance and leads to fatty liver disease. This is why fatty liver is essentially prevalent in everyone who is insulin resistant. If you're fat but your liver isn't, then the proverbial spillover has not yet occurred, meaning you can store more energy in the adipose tissue. Once it's full, the fat spills over onto the liver. Insulin also prevents the production of glucose in the liver, known as gluconeogenesis, but with defective insulin signaling, the liver is not only taking up glucose and not storing it, it is also producing more glucose. This is the beginning of the hyperglycemia that is the hallmark of diabetes. Finally, we have the skeletal muscle. One reason why exercise is so good for insulin sensitivity is that it promotes glucose uptake into the muscle. The muscle accounts for the majority of glucose coming from a meal, and it is the most powerful determinant of metabolic rate. It's extremely protective against energy toxicity since it burns and stores so much of it. If the muscle becomes insulin resistant, the rest of the body is done for. Since the liver has been feverishly exporting fat, the muscle takes up a lot of these fats and burns them for energy. With the massive amounts of energy that needs places to go and the systemic inflammation that has been culminating, not even the muscle can spend or store all of the energy. Instead, the incomplete lipid metabolites accumulate and induce insulin resistance in the muscle. This means the muscle has a reduced capacity to be the glucose reservoir it normally is. Now, the hyperglycemia becomes worse and type 2 diabetes is inevitable. Every problem just gets worse from here. The high insulin makes insulin resistance worse and vice versa. Now that there is more glucose in the bloodstream, the liver naturally takes up more of it since it can do so independently of insulin. However, since it can't store it as glycogen, it creates more fat from it. The fatty liver becomes worse and inflamed, eventually leading to permanent liver damage. Hyperglycemia will also directly lead to the production of more reactive oxygen species, which will inhibit the mitochondria from burning fat for energy. This also means the antioxidant system is compromised since it has to deal with a greater burden of oxidative stress. So oxidants throughout the body have a much greater capacity to damage tissues. It also leads to more reactive oxygen species in the mitochondria itself, which leads to more inflammation and all of the problems that are associated with that. Insulin is also needed to maintain muscle mass, but this can no longer happen either because of deficient insulin signaling. Instead of using energy to build or maintain muscle, muscle ends up breaking down, meaning it has less of a capacity to take up more energy, making everything worse. This is a body at war with itself. Everything the body attempts to do to make the problem better makes it worse, and different parts of the body can't communicate properly with each other. The body becomes overloaded with energy, yet able to use so little of it. The body continues damaging itself from the inflammation, yet is getting signals to continue the immune response. Worst of all, the last thing the body needs is more energy, but it constantly thinks it is starving and needs to store energy. Unfortunately, this is a problem that needs to be corrected at a systemic level, costing lives and dollars. We have let the ruthless transnational organizations have their say on what we should eat and are brainwashed to keep eating it. Then they have medications that barely keep you alive, but sick enough to live and make a profit off of. It all starts with insulin resistance. In the next video, we'll be looking at all the consequences of this condition. Don't let them fool you. Subscribe to our channel. Also, give this video a like if you enjoyed it. We're going to have a lot more videos on insulin resistance and relating topics coming in the near future.